microchip technology. Coffee Break is our ongoing forum in which we discuss new and evolving technology, all in about the amount of time it takes to drink a cup of coffee. I'm your host, Eric Gladfelter. Joining me as usual is our moderator, Aliyah Fahout. Hello, Aliyah.
Hi, everyone. Thank you for joining us today. We are currently live on YouTube, Facebook, and LinkedIn. And you can participate in today's episode by leaving your questions and comments in the chat, or you can email us at livestream@microchip.com after the broadcast. If you're watching on YouTube, you can ask questions in the chat. Make sure to subscribe and click the bell so you know when we're live and when our next episode is. And on LinkedIn, you can submit your questions in the chat and subscribe to the event to get all information related to the episode. Back to you, Eric.
Thanks, Aliyah. Our topic today is I3C, a next-gen two-wire interface. Joining me in the studio are Toby Sinkinson and Stephanie Pinthrick. Toby, you've been here before. Stephanie, your first time. Welcome to you both.
Thank you, Eric.
Yeah, thank you.
All right, before we talk about I3C, Toby, let's talk a little bit about I2C. Why has that been so successful?
Well, yeah, it's been 40 years out there, right? So, and one of the main reasons that I2C is so successful is that it's a standardized protocol. You have very clear ways of sending data and commands, and after 40 years, you have lots of different products out there that support it. You're probably not going to run into a problem that's never been seen before. Right. It's very reliable in that way. And there's been innovation in I2C. You had 20 years after it came out, you had the SM bus for smart battery management. This showed you how you could interoperate over an I2C bus. So it's very reliable. It's a terrific protocol for serial communication.
Okay, so Stephanie, with that standardization of that protocol, that has enabled the deployment of I2C as a module or a peripheral in many different types of devices, right?
That's correct. It could be found literally on all our microcontrollers and microchip. And integrated circuits, sensors, and other electronic components are designed with I2C interfaces as well. Okay. Throughout the industry. Okay. And at Microchip.
So if it's so successful and so reliable and is so ubiquitous, why do we need I3C?
Well, a lot of it has to do with the way industry is headed and where our devices are going to be, the needs of future devices. So when MIPI came together to create a new, improve the protocol of I2C, they knew that future designs are going to need to support more sensors on a bus. They're going to need to fit into smaller spaces. They have that space constraint. You'd want to bring down the power. I2C is a lower power, but you can even get lower than it is now. And to have a faster data transfer is something very important. Yeah.
Okay,
yeah.
So like many things in electronics, we want more data, lower power, smaller footprint.
That's right, yeah.
All right, so what does I3C deliver in those areas?
Well, they fall into three main buckets. You've got improvements in speed, you have improvements in power consumption, and you have improvements in flexibility. Okay. In terms of speed, the data rates between I3C and I2C are a huge improvement. So it's a 30x improvement in terms of the number of bits per second you can send. And mainly that's because in I3C, the spec allows you to run your clock up to 12.5 megabits per second. There are some faster data rates that are available as well, but this is the baseline. This is a 30x improvement in terms of data transfer. And then in terms of power consumption, one of the key features in I3C is you can operate at a lower voltage domain. And to get an idea of how much power savings you have by operating a lower voltage domain, you can see here at the 3.3 volts, both I2C and I3C are shown there, I3C in orange. You drop drastically when you go down to 1.8 here. And now we've added an even lower voltage domain for I3C. But even within a single domain, you can see the blue I2C bar is much higher than the orange I3C bar, and that's because of the way the I3C, the bus is configured. So you can actually, most of your transactions in I3C will happen in a push-pull configuration like you have in SPI. This allows you a faster rise time so you can go faster, but you're also not consuming power through those pull-up resistors, so it's way lower power. So that's a huge improvement there.
Okay, so you also mentioned flexibility. So walk us through some of the options that you have and what are the design considerations that people need to be aware of?
Sure. So just as I2C kind of standardized the way that you're sending data and commands, I3C standardizes the way you handle your events, your typical things that happen on the bus. So all I3C devices need to be able to support these commands, these new. And so one of the maybe the most exciting ones there originally is the dynamic address assignment. You don't have to now depend on those static addresses that are assigned in I2C. You're not stuck with that, or even if there's an alternate. So you don't have these collisions if you have multiple of the same sensor, or if inadvertently two vendors happen to select the same address. So there are ways around that, but that dynamic address assignment really makes that much better. And then, another key piece here is that I3C is a true two-wire bus. You have all of your interrupt signals can now happen on that bus. You don't have to have separate signal paths as you do in I2C to send interrupts. You can now, there's commands that allow you to reset devices as needed. And also, devices can be powered off, right? They can to save power, and then when even though that bus is already configured, they can power on and be able to join the bus. They'll just receive that dynamic address because the controller has that ability now. So there's also built-in error detection as we're going along that wasn't available in I2C, so that's a nice feature. So a lot of long-term thinking going on here.
Sure.
That's why I love working on this stuff. Is that so? And one of the ways that they were that MIPI was thinking about this is that they knew you had 40 years of developing all these I2C sensors. You weren't going to suddenly have a plethora of I3C. So you needed to have a way to phase that in. So what they've done is they made sure to allow you to share a bus with I2C and I3C devices. So you could replace things as needed. So it's very cost prohibitive to replace all of those devices, to change all of your layout at one time. But because you can phase this now, you have a lot of flexibility there.
Okay, so you can add a device that with an I3C module into a bus that has a plethora of I2C modules.
That's right. Yeah. Okay. Your main communication can be an I3C, but you can still be able, if your I2C sensor isn't support I3C, then you can still have it there and work with it.
Excellent. Now you mentioned MIPI, so that's MIPI Alliance, so that's the standards body.
That's right. These were a group of key players that were aware of all the problems the challenges for I2C and what devices are going to need in the future. They came together, started writing this script back in 2013.
Okay. Okay. So this is now a standardized module. So if somebody wants to start working with this, can they get a hold of it today? Do we offer parts with this module in it?
Yes, we definitely do. The device family is called the PIC18Q20. It's the industry's first low pin count microcontroller with I3C support. It comes in low pin counts, meaning it's available in 14 and 20 pins, in packages as small as 3 by 3 millimeters. So it's very suitable for space constraint designs. Microchip developed this product family with advanced serial communication interfaces and includes up to 2 I3C target peripherals. This is for high-speed data transfers and communications with multiple buses.
Okay.
Other things that this part has is supports multiple voltage domains. So in embedded systems, they are comprised of numerous components from integrated circuits, sensors, and other electrical components. And many times they need to connect to one another. However, they operate at different voltage domains. Where MVIO, or multi-voltage I/O, comes in, it resolves this voltage incompatibility and removes the need for external level shifters. Essentially, MVIO is internal level shifting.
Okay.
So this is really nice, and the fact that I2C and I3C can operate at separate voltages simultaneously. So the I3C bus can run it down to 1 volt, and while maintaining the I2C bus at a higher voltage like 3.3 volts for compatibility with legacy devices. So really the PIC18Q20 acts as a bridge device.
Sure. Okay.
So the other things with this product family is it has the slew of core-independent peripherals that we find on all our 8-bit products, as well as all the low-power features. So these CIPs, or core-independent peripherals, can be combined and interconnected together to create custom functions for your specific applications. So bottom line is with I3C, the MVIO, and all the CIPs, the PIC18 can reduce BOM cost, system complexity, and the overall system cost of your designs.
Okay. So if somebody was interested in this device, what's the best way to get started?
Sure. Eric, the best way is using the Curiosity Nano board, and I have an example here of what it looks like. It's a very compact, fits in your pocket development board that has access to all the I/O pins. It has integrated programmer and debugger, and it can be used with Microchip's entire ecosystem, so MPLAB X, MPLAB MCC, or a code configurator to generate code, and we have the whole driver suite with the MVIO and I3C, so developers can access this all through the MCC interface. And we have a whole bunch of code examples to help you get started and to essentially rapid prototyping with this board.
Excellent.
Another thing is we've partnered with Binho, who creates a I3C logic analyzer. So this basically allows you, when you do purchase a board, you get a 45-day free trial of this logic analyzer, and it assists with your debugging your I3 signals. Okay. So again, all in all, these things help expedite your projects and getting your design in place.
Excellent. Okay, so we have a very fast, very flexible, very low power new protocol based on an existing ubiquitous legacy protocol, and we have this in a new microcontroller that you can get today.
Yeah, definitely. And so, as you know, if you want to be able to innovate for the future with your device, you have this ability to be ready for that. You implement it in a phased approach. There's a lot of flexibility there. It does, just because of the cost prohibition, doesn't need to impede your progress towards innovation there either.
Excellent.
So, yeah.
And I just wanted to add that we've just touched on just really a high level of I3C in this session. There is a whole bunch of resources at Microchip that we have to help you get started with your design. To learn more about I3C and the PIC18Q20, those links will be provided in the video description. So all things will be there in terms of like code examples, technical briefs, applications to help you get started. As I mentioned earlier, that the Q20 has all the protocol, communication protocols for the legacy, and so it's excellent as a bridge device, and it has the MVIO feature, which helps reduce your BOM cost.
Excellent. So it sounds like we have a full set of material to make it easier for a designer to implement with this new protocol. Excellent. Stephanie, Toby, thank you so much for sharing your knowledge about this topic. At this point, let's go to Aaliyah and see if we have any questions from our viewers today.
Sounds good.
Thanks, Eric. We do. Our first question is from Peter online, and it is I3C completely backward compatible with I2C?
It's not completely compatible. Like we said, there's a lot of benefits that you can share the bus, but there are situations where it's not. For instance, like in what you were describing, Stephanie, that if you have I2C sensors that typically operate at 3.3 and 5 volts, but you're running your I3C bus at 1.8 or 1.2, then those devices can't be on the same bus. So I think having the PIC18Q20 is a great way to kind of transition until those sensors are able to have those lower voltages. You can actually start getting your design for future ready there. Also, with it in I3C, your controller has sole control of the clock. So if you need to have clock stretching because the device is taking more time to finish the transaction, you can't pull the line low and say I need more time. So that's something to think about. But again, that PIC18Q20 is a great bridge for that situation. Yeah.
Mm-hmm.
Thanks, Toby. Your next question is from Lisa, and it is, for the design of new devices, are there any I3C certifications that need to be passed?
Actually, no, there aren't any certifications. There is a conformance suite, these kinds of tests that you need to be able to show that you can support all the different kinds of transactions on the I3C bus. But one important thing here is that MIPI actually sponsors a PlugFest, which is this interoperability event where engineers from competing manufacturers come together and they have an opportunity to test your device in the real world, not just with the conformity suite, but with actual other devices. So it's a nice place. It's a neutral ground. There's an NDA coverage, but it allows us to sharpen each other's devices and innovate together. Yeah, it's pretty cool.
Great, thank you. This one is coming from Randy online, and it is, how fast is the industry moving to I3C?
Well, I3C was originally released in 2016, so it's been a little bit of time, and that's enough time now that all major chip manufacturers are coming out with devices with I3C support. It's clear that this is where things are going. Industries like the mobile industry, where you have that small space constraint, also some lower power constraints there too, are probably going to move fastest. You don't have to have those extra signal paths and so on and so forth. Your layout can be simplified. But other industries like data centers, where you're operating at scale, that kind of power savings that you get with I3C over iSqueed pays dividends, right? Environmentally and economically. So.
And so I just wanted to add that for additional resources, we do have a microchip podcast called Beyond the Microchip that kind of covers I3C and the data center applications. So it's a good resource to get more information.
Yeah, great. I loved that series. And then, also major chip manufacturers have also adopted I3C as a standard for IoT devices. So we'll see that there. But ultimately this does come down to how quickly devices are available that you can add, and then your validation and those sorts of issues too. Sure. But it's here. We're ready to go.
It's here to stay.
Yeah.
So a key feature really with the, as Toby mentioned earlier, with I3C is backward compatibility to I2C. And this is really key to essential to systems adopting it in their design. So all I3 systems, or all I2C systems can be designed to I3C. It's just a matter of adding, when they're ready to upgrade, they can do it without breaking their current system.
Okay.
So that's a nice feature.
Yeah.
Thank you both. This question is coming from PLC Worker on YouTube. What advantages does I3C have compared to SPI?
Well, in SPI, you've got, you have the 4 wires that you need to do those transactions. You can go faster with SPI than you can in I2C, but so I3C sort of fits in between that. You get to your true wire bus, but you can go faster than I2C. So those are the kinds of things. But that, especially if you have also with SPI, right, it's not standardized. So you have a lot of different implementations of SPI, so you can't swap things in. You have to, it takes more attention there. I mean, there's a use case for every serial protocol, but yeah, those are some of the key differences that you should keep in mind.
Awesome. Thank you, Toby. Next question is from Ernesto. What would you say are some design challenges that a system designer should be aware of?
Well, in I3C, your bus capacitance is limited to 50 picofarads. So compared to I2C, it's like 400 picofarads. You're talking about shorter cable distances. You need to pay attention to the PCB trace. But most of what we're talking about, where these trends is leading us, you're in that space constrained space. This is very easily met, but it is something you have to pay attention to. Yeah.
Great, thank you. Another question is from Alyssa. Why did Microchip design a target-only device?
Really, the reason why we designed it is we had a lead customer, and so it was very application specific. In their particular application, they needed to talk to 2 different controllers. But we made this device so that it can again be a bridge device, so it can be used for current design as future proofing as you want to add I3C to your designs.
Thank you. I think we have one last question here. Let's see. Oh, no, it looks like those are all the questions I have for you today, for both of you. So for the audience out there, if you have additional questions and comments, you can email us at livestream@microchip.com after this broadcast. And don't forget to subscribe to our YouTube channel and follow us on LinkedIn. Back to you guys.
Thanks, Leah. Stephanie, Toby, thank you again. Thank you to our viewers for taking some time out of your day to join us. Please visit us at microchip.com/coffeebreak. You can see our remaining episodes for the rest of the season. You can sign up for notifications, and you can link over to our library of previously recorded sessions. Thank you for your time again, and see you next time.